Hello, everybody, and welcome to CPFD's webinar, Introduction to Barracuda Virtual Reactor. My name is Sam Clark, and I'm the product manager for Barracuda, and I'll introduce you here to Rosemary Clark, who is a senior support engineer at CPFD. And we'll be doing this webinar together, and so Rosemary will kick us off with these introductory slides, and then I'll rejoin for doing the live demo portion. So here you go, handing it off to you, Rosemary.
All right, thank you. Thanks so much. All right, so this webinar is being recorded. So if you miss anything or you want to share something you saw with a colleague or a friend, you'll be able to do that. And the recording will be posted on our webinars and presentations page under the resources tab in the next day or two. And we will also send out a follow-up email after the webinar with the link to the recorded webinar. And we'd also like this webinar to be interactive, and we need your help to make that happen. As you think of questions during this presentation, please put them in your question panel. We've intentionally allocated time to address questions after the presentation, and we've also put some links in the chat window that will be showing during the presentation. So just if you want to look at your chat window, all of those links are in there. In the webinar today, we'll cover a broad range of topics related to virtual reactor, including an introduction to CPFD software, a summary of the industries and applications for which people use Barracuda, and an overview of what makes our modeling approach different from other software. We'll also do a demo of virtual reactor so that you can get a feel for how the graphical user interface works, how the solver runs, and how simulation results are analyzed using our bundled post-processor TechPlot for Barracuda. By the end of the presentation, you should have a good idea of what Barracuda does, how it works from a high level, and whether it is a good fit for your simulation needs. Here at CPFD Software, we are advancing multi-phase simulation and technology. We are the inventors of the Barracuda Virtual Reactor product and have been focused on developing multi-phase simulation technology for over 20 years. Our team includes chemical and mechanical engineers with decades of experience in fluid particle systems across a range of industries, as well as software developers specializing in physics modeling, numerical methods, GPU programming, and user interface design. CPFD's headquarter offices are located in the energy corridor of Houston, Texas. From a commercial perspective, CPFD engages with customers and partners in a variety of ways. We license and support Virtual Reactor for those who want to use the software in-house at their own companies, and we provide engineering services where we set up, run, and analyze simulation results. We provide training to people who want to learn how to use Virtual Reactor, and we collaborate with companies around the world in a variety of research and development projects related to fluid particle flow and modeling. CPFD also has a worldwide network of distributors who provide software licensing and support services to customers outside of the United States. CPFD's flagship product is Barracuda Virtual Reactor, a physics-based engineering software package that simulates the 3D transient behavior in a fluid particle systems, including the multi-phase hydrodynamics, heat balance, and chemical reactions. It is a purpose-built to model chemically reactive fluid particle flow and is the only commercial software package focused specifically on this area of modeling. A Virtual Reactor is a full software package that includes a graphical user interface, a grid generator, solver, and post-processor. We've designed our GUI to be efficient and logical for users setting up simulations. Our solver is extremely stable and fast, and TechPlot for Barracuda, our bundled post-processor, offers state-of-the-art visualization and data analysis capabilities. Virtual Reactor runs on either Windows or Linux and is optimized to use NVIDIA GPU cards for incredibly fast parallelized calculations. One broad category of systems that Barracuda Virtual Reactor is used to simulate is chemical reactors with particles flowing in gas domains. Many industrial fluidized bed reactors fall into this category including this example shown here, which is an FCC regenerator modeled with virtual reactor. Note that this is a full-scale, three-dimensional transient simulation. The system in this example is 75 feet tall and has a vessel diameter of 19 feet. For this type of simulation, the flow is modeled as compressible, and an unlimited number of gas and vapor materials can be used in this flow domain. Particles can contain solids, liquids, and volatiles, and each particle species can be represented with a full particle size distribution. Thermal calculations are supported, and chemical reactions can be specified by the user. Reactions can involve all gas and vapor species in the flow domain, as well as solid and liquid materials in the particles. The other broad category of systems that Barracuda Virtual Reactor is used to simulate is chemical reactors with particle and gas bubbles flowing in the liquid domain. The example shown here is an industrial scale ebulated bed reactor with a height of 120 feet and a diameter of 12 feet. For this type of simulation, the flow is modeled as incompressible, and the flow domain is composed of multiple liquid materials. Gas and vapor bubbles, along with solid particles, are flowing within the liquid domain. Each particle and bubble species can be represented with a full-size distribution as well. Mass transfer of gases and vapors from the bubbles to the domain is possible by using evaporation and gas absorption models. Thermal calculations are supported, and chemical reactions can be specified by the user. Reactions can involve the liquid materials in the flow domain, absorbed gases, and solid materials on the particles. Engineers around the world use Barracuda Virtual Reactor to simulate chemical reactors in a wide variety of industries. In the refining industry, virtual reactor users have modeled systems such as FCC reactors and regenerators. Engineers working for petrochemical companies have modeled reactors for polyolefin and acrylonitrile production. Other virtual reactor users have modeled biomass and coal gasifiers, including both fluidized bed and entrained flow systems. In materials and chemicals, virtual reactor is used to model reactors that produce titanium dioxide and other valuable products. Virtual reactor is also widely used to model calciners and other reactors used in cement production processes. Power generation companies use Barracuda to model circulating fluidized bed combustors and other power generation reactors, using fuels that range from coal to wood to alternative feedstocks. Engineers at the forefront of the development of clean technologies and renewables turn to Barracuda to model processes such as carbon capture, waste to fuels, hydrogen production, and advanced recycling of plastics. Researchers in fundamental fluidization use virtual reactor to design experiments more quickly and effectively and gain deeper insights and understandings by complementing experimental results with computational models. See the webinars page on CPFD's website for a number of industry-specific customer stories about virtual reactor. Barracuda Virtual Reactor is used to improve the reliability and performance of chemically reacting industrial fluid particle systems through simulation. These industrial units typically operate around the clock, and in many cases, they are key components of continuous processes intended to run for years on end. If a reactor is underperforming due to fundamental design problems, the long-term loss in productivity could reduce profits. In extreme cases, design issues can cause damage within a reactor and result in catastrophic failures of mechanical components, leading to very expensive unplanned shutdowns. For operating units, virtual reactor simulations allow you to look inside the system in a unique way, determining root causes of underperformance, and use virtual testing to reduce the risk of making any changes. And often, as you are looking at the software results, other ideas come to mind and additional optimization opportunities are identified. For those of you developing new technology, Barracuda is used to accelerate and broaden that R&D and then quickly commercialize, scale up, and communicate the unique capabilities of your technology to customers, partners, and others. Hundreds of peer-reviewed journal papers have been authored by engineers and researchers using virtual reactor to simulate fluid particle systems in a wide range of industries. We have created a searchable database of these publications on the CPFD website and encourage you to explore publications related to applications of interest to you. Odds are you'll find several high-quality articles that show how virtual reactor users have gained valuable engineering insights into their systems. These publications are often very useful as you get started using virtual reactor, since many discuss details of model setup such as boundary conditions, physics model settings, and chemical reactions that could be directly relevant to the work you are undertaking. We upload information about new articles on a regular basis, so make sure to check back periodically to see the most up-to-date industrial and academic publications about virtual reactor. The CPFD approach used to model multi-phase fluid particle flow in Barracuda Virtual Reactor is an Eulerian-Lagrangian method. Building upon a unique heritage from Los Alamos National Laboratory, CPFD software expanded fluid flow modeling to the simulation of industrial-scale fluid particle systems, leveraging the 3D MPPIC approach. The fluid phase is modeled with the Eulerian approach, which means it is treated as a continuous domain and is solved using a Navier-Stokes approach on a computational grid. This is the same fundamental approach used by the vast majority of traditional CFD solvers, and for good reason. It allows for efficient and accurate simulation of fluid flow, and the numerical methods for solving the flow equations are well known. Clouds representing particles and bubbles are modeled using a Lagrangian approach, which means they are discrete entities that can be located anywhere in the domain. We say that the clouds are gridless in this sense because they can and do travel between the computational cells according to the physics calculations of their movement. The CPFD approach is bidirectionally coupled, which means that the fluid affects the particles and bubbles, most importantly via drag forces, and the particles and bubbles affect the fluid, for example, by occupying physical volume within the cells and inducing a pressure drop based on drag forces. This coupling is tight and implicit, which means that the interphase effects are accounted for in every cell and at every time step of the simulation. Virtual Reactor is able to accurately simulate the behavior of industrial scale systems in a fast and efficient manner. Virtual reactor simulations can use hundreds of millions of particles, and it is possible to fully capture the size, temperature, composition, and position of particle and bubble species. The ability to account for particle size distributions is a distinct advantage of the CPFD approach when compared with fluid-only approaches such as the two-fluid model, because the entire PSD, not just the D50 or the solder mean diameter, can be important for predicting fluidization behavior. Another advantage of the CPFD approach is that it naturally supports a wide range of particle loadings. Within a simulation, particle volume fraction can range from dense, such as in a bubbling fluidized bed, to dilute, for example, in a lightly loaded cyclone. The CPFD method calculates energy and mass transfer between fluids, particles, and bubbles. This includes convective and radiative heat transfer, as well as chemical reactions that can transfer mass and energy between the phases. These calculations are tightly coupled with the hydrodynamics solver, allowing virtual reactor to accurately model the behavior of chemically reacting systems. In this presentation, we've intentionally avoided diving into any mathematical equations or detailed descriptions of the numerical methods used by Barracuda. Instead, our goal here is to give a high-level introduction and overview of the CPFD approach so that you can have a good idea of what makes Virtual Reactor different from other CFD tools. If you're interested in learning about the details behind the CPFD approach, we encourage you to visit the Publications about Barracuda Virtual Reactor page on our CPFD website. You'll find a listing of many peer-reviewed journal papers that have been published by CPFD's development team and experts that we have collaborated with over the years. covering a range of topics including coupling between particles and fluids, wall treatment, methods for calculating thermal behavior and chemical reactions, and much more. CPFD develops Virtual Reactor to run on both the Windows and Linux operating systems. This allows engineers to use Virtual Reactor on systems ranging from Windows workstations sitting under their desks to high-performance Linux computing resources common in data centers. Barracuda supports the use of NVIDIA GPUs to perform highly parallel physics computations, which enables simulation speeds that rival the performance of expensive multi-node clusters. Compared with running Virtual Reactor in CPU serial mode, running with a single GPU on either Windows or Linux can give speedups of 100x or higher. Multiple GPUs can be used to further accelerate calculations on Linux, resulting in speedups of 500x or more compared to CPU serial calculations. CPFD partners closely with NVIDIA to ensure that Virtual Reactor runs as efficiently as possible on the latest generations of NVIDIA hardware. We also partner with Mark III systems to ensure that Barracuda users have access to top-of-the-line hardware if they choose to run Virtual Reactor on-premise. And we work with best-in-class cloud computing providers such as Rescale, Microsoft Azure, and Amazon AWS to fully support Virtual Reactor users who choose to run simulations on the cloud. Depending on your project needs and IT infrastructure, it might make sense to run Barracuda on-premise, in the cloud, or a combination of the two. And CPFD has developed Virtual Reactor to flexibly support either approach. Now I'm going to hand it over to Sam Clark again, the Barracuda Virtual Reactor Product Manager. He's going to go through a live demonstration. He'll show how to use the graphical user interface, as well as a few details about running the solver and using TechPlot for Barracuda.
Okay, thanks, Rosemary. Here, I'll go ahead and drop out of PowerPoint here, and you'll see I have our latest release of Barracuda installed on my laptop here, and this is a Windows laptop. It does have an NVIDIA GPU card in it, so we'll be able to see a little bit about how that works with Barracuda. This is our release from the end of the year 2022. One thing that we're pretty regular about is releasing about every 6 months a new version of Barracuda that has new features, new capabilities. So that's our general release cycle. Here, so I'll go ahead and open up a demonstration case here. And this case is from our new user training class. And this is a coal gasification example that is a fluidized bed reactor. And so here, what I'll do is I'll just walk through a few of the important areas of the GUI that people often have questions about and highlight a few features. The first thing I'll point out, as Rosemary mentioned, our GUI is fairly logically organized, and one of the organizational tools is on the left here, the project tree. So users start at the top of the tree, they work through all the dialogues for any of the features that they wish to use. And then by the time you get to the run menu, you're ready to start the simulation, and then post-run is for post-processing. So the first window here that I'll highlight a little bit is the setup grid window. Barracuda uses STL files as the input for our three-dimensional geometries. And so we have a lot of integrations with TechPlot for Barracuda that I'll point out as we go along. The first one here is this View STLs button. So I'll go ahead and click that. And what you'll see is a lot of these buttons in Barracuda, they open TechPlot with some sort of predefined view. This is a predefined view where we can open the STL file, we can rotate it and zoom in and things like that. So I'll go ahead and get out of here. In this interface, what you would do as a Barracuda user is define your computational grid lines. And so here are these blue lines and black lines that are overlaid on the three views of the STL file are defining where the computational cell edges will intersect the STL, and then they will eventually define the computational cells of the model. And Barracuda does come with its own grid generator. So here I'll go ahead and click that. We can generate this grid. This is a fairly small grid. I think once it runs, we can see that the number of real cells is about 78,000 cells. So this is not a huge model by any means. This is a training example that we use to just get people familiar with how Barracuda works. If we click the View Output button now, we can see what our gridded geometry looks like. We can make sure that we've captured all the internal structures, such as the cyclones and the heating coils and the gas sparger. So again, just one of these predefined views that lets users quickly evaluate how the grid definition looks. Another window that I would like to highlight is the base materials window. And so one thing that Barracuda has is a built-in library. This has several hundred materials that are already predefined in terms of their physical properties, like molecular weights, heat capacities, things like that. A typical Barracuda project will probably only use something like 10 to 20 of those materials on average. There's no limit to the number of materials that you can use, as Rosemary mentioned. But I would say this is kind of typical, right? A lot of times people have multiple solid species, multiple gas species, and all of these can be involved in the chemical reactions that are defined by the user. For each of these species, there's a base materials editor where you can go in and you can define all of the physical properties. This is a gas, so we can define things like viscosity and heat capacity and all of these sorts of things. And so this interface is common among all of the different types of materials that are used in Barracuda. If you have a material that is not already in the base material library, there's also the possibility of adding a material from scratch. And so that's a capability as well. Next, let's look in the particles section, since we are always dealing with systems that have particles in general in Barracuda. One of the more important aspects of models that include fluids and particles is the drag models. Barracuda comes with here are these 11 drag models built in, and so these cover a wide range of needs that people have, but we also have some flexibility where you can create your own drag model if you need something different than these ones. As an example, I'm going to copy this Winu-Ergen blend model, and we'll edit this just to illustrate. Barracuda has a user-defined expression interface that allows users to define constants, define calculations based on either these constants or a wide range of built-in variables that are available to reference. So this is quite flexible. It's possible to define almost any drag model that you would need using this sort of user-defined expression interface. Okay, I'm going to go ahead and delete that one just so I don't change my project. Okay, the next thing I want to point out is in terms of particle species. So when you define particles in Barracuda, one thing you'll see is that you can have multiple species of particles. They can all have different physical properties, different compositions. So here, let's take a look at this fresh coal feed species. In this case, we can look at the applied materials. We can see that this is 5% ash, 45% carbon, and 50% volatiles in this example. And so the particle density is based on the mixture of materials in the particle. When you have volatiles, you can actually define the particle density because volatiles are a little bit more nebulous in terms of their properties. The other thing that Rosemary had pointed out earlier was Barracuda's support for particle size distributions, and this is really important for a lot of simulations. The way that size distributions are defined in the interface is through this tabular format. And so we can see cumulative mass percent versus particle size in diameter with units of microns. This is another part of the interface where we have a button that's connected to TechPlot, so I'll go ahead and click that. We can graph the particle size distribution. TechPlot supports both three-dimensional plots like that show the geometry, and it also supports these sort of XY plots for more traditional kind of data analysis. And Barracuda does output a number of data files that are useful for that type of plotting. Another area that I'd like to point out is just boundary conditions. And so for all CFD models, and Barracuda simulations are no exception, the boundary conditions are extremely important. Barracuda supports a wide range of different types of boundary conditions. We have pressure BCs, which people usually use for like outlets from their system. Flow BCs and injection BCs are often used as inlets for fluid flow or particle flow. Thermal wall BCs are used for things like heating coils or walls that are being cooled in some way. So quite a bit of flexibility in terms of setting those boundaries. If we look at one of these as an example, most of the boundaries follow this sort of pattern where we have these tabs that guide us through the various things that we can set up for the boundary. You have to tell Barracuda where the boundary is located in physical space, and so there's kind of this interactive view where you can define exactly where your boundaries are intersecting the STL or the computational grid. So that's pretty common on all of these boundary condition definitions. All of the boundaries support flux planes, which are data output mechanisms that write fluid flow rate, particle size information if you select it, fluid species information if you select it. All of these can go out to text-based files that can then be analyzed either through TechPlot or through a scripting language like Python. So a lot of users do a lot of good data analysis from flux planes. At pressure BCs, flow BCs, and injection BCs, you can also introduce fluid into the system. Some of them support letting fluid exit the system. Particles are similar. Depending on exactly what you need, you can either feed particles into the domain or you can let them exit the domain either freely or at a specified rate. So a lot of flexibility there to model what's really happening in these chemical reactors. The other thing that's really important to a lot of users of Barracuda is chemistry. So Barracuda, the interface, supports the concept of chemical reaction rate coefficients, and we basically use these as building blocks to define our overall reactions. And so here, if we look at one of these rate coefficients, this is kind of a common form that a lot of people use in Barracuda is just Arrhenius rate coefficients. And so some sort of pre-exponential constant, dependence on temperature, activation energy, dependence on the amount of carbon on the particles or the amount of carbon in the computational cells. There's a lot of flexibility so that depending on how you have formulated your chemistry, you can get that into Barracuda through this interface. This is another area of the GUI that also supports user-defined expressions. And so this is similar to that drag model expression interface, but in this case, the variables that are available have more to do with the species in the system and how they would typically affect chemical reaction rates. So that's another user-defined input that the Barracuda GUI supports. For reactions themselves, we'll see something like this pretty commonly. These are volume average reactions, which in Barracuda's internal workings means that they're solved more from the perspective of the computational cells. We also have a concept of discrete particle reactions, which is more focused on the reactions from the standpoint of the particles. And so it's flexible, right? You can choose whichever basis makes the most sense for your case. If we take this first example, this is carbon combustion, so carbon plus oxygen going to carbon monoxide. This is kind of a simple reaction rate here. We're using one of our building block rate coefficients, and it's multiplied by the mass or the mole concentration, excuse me, of oxygen in the cells. And so this is a pretty common pattern that we see as well in Barracuda chemistry input. As we're seeing here, this particular example has 9 reactions that are defined. There's no hard limit on the number of reactions that you can have, but I would say most people typically have something like 10 to 20 reactions is pretty common, right? It's kind of unusual for people to have hundreds of reactions in Barracuda. And so a lot of times people can come up with a global reaction set or a simplified reaction set that represents what they need in their system. and gets to this order of magnitude usually. If we go down here, we can look at the data output section. And as Barracuda runs, it has a lot of different options on information that it can produce about what's happening in the simulation. We have everything from flux planes to visualization data that this all gets output to TechPlot, so you can visualize it in 3 dimensions. A lot of different output variables are available, and the GUI allows you to select just what you need on the output to try to make the files a reasonable size. You don't want to fill up your hard drive too fast, and that's definitely possible to do because Barracuda has so much potential information available for output. Barracuda can also do time averaging of data, and this is often very important. As Rosemary mentioned, Barracuda simulations are by nature transient simulations, and so they never reach a pure steady state in the sense that some CFD codes solve for steady state. Barracuda does not. So by time averaging, we can get an engineering conclusion that's effectively steady state information or pseudo steady state. Barracuda also offers data output on predefined planes, specific points in space. These are often analogous to things like thermocouples or pressure taps that have really high frequency data output at specific locations within the domain. So those can be really useful. Barracuda has a wall erosion model that's been very successful. A lot of information is available to come out of the solver. So as I mentioned earlier, once the user sets up all of the information that they want in their model, you get to the run page. This is where you would select how Barracuda is running the solver. Barracuda does support running on multiple CPU cores. However, the way that most people run Barracuda is purely on the GPU. And the reason for this is that GPUs have so many cores, they're so highly parallelized that the best possible performance is generally, if you have a GPU card, you should use that, and that will make the solver run, as Rosemary mentioned, is something like 100 times faster is often what we see on a single GPU card, or multiple hundreds of times faster if you have multiple GPU cards on Linux. So once you get to this point, you can select the mode that the solver is running in, and then we often tell people to run the solver setup. So I'll go ahead and click on that now. And what you'll see is the solver pops open on your system's terminal. And there are other ways to run this as well. You can automate it for batch systems and things like that. It'll ask you which GPU card, if any, you want to use. So here I'll just say I want to use this GeForce GTX that's in my laptop. You'll see the solver start running time steps. And in a setup mode, it basically runs one time step and then it stops. And then you can click the View Setup button. And really what this does is it helps you to verify that your boundary conditions are set up correctly. That's what this default view is for. So in this case, we can see our pressure BCs are defined on the cyclone inlet horns. They are connected with BC connectors down to flow BCs at the bottom of the cyclone dip legs. And so this is a way of modeling internal cyclones or approximating their behavior. We have flow BCs that are introducing fresh coal into the system. We have a flow BC that's at the bottom that's bringing in steam. We have this set of injection BCs that is approximating or modeling the behavior of a large gas sparger. And we see this pretty often too. In Barracuda, we're often modeling really, really large systems. And so it's not really possible in a lot of cases to get down to like nozzle level details. So these injection BC points are really a nice way of modeling big things or big sets of fluid input in those types of cases. These bright pink surfaces that we see here, these are representing a thermal wall that is on these heating coils inside of this fluidized bed. So these are supplying energy to the system to promote the gasification reaction. So that's another view that we can see. I'll go ahead and get out of here And one thing I want to show is a model that's already been run. So in this case, this was just showing how the model would typically be started up. So I'm going to go ahead and switch out of here, and let's go to the pre-setup that's already been simulated. And I just wanted to point out here in the post-run menu, similar interface here, but instead of view setup, we'll click view results. And this is where the tech plot view that pops up will show us the most recently created results files. In this case, this simulation ran out to its end time of 100 seconds. And so we're seeing the particles colored by volume fraction at that point in time. And so this is a way of expressing particle concentration, right? How much volume is being taken up in each cell by the particle phase. And so once you start getting into these views, these quick macros can be really useful on the side. Once more, we can look at cells colored by a number of different output variables, such as pressure, fluid velocity, fluid temperature, a number of different things there. Particles, we can color them by speed or size or residence time. So there's a lot of different information is being carried around on both the fluid phase and the particle phase. And so you can do some really nice analysis of the results here. You can also, what we're seeing here is one results file loaded in. You can also load in all of the results files from a simulation and make animations. All of that stuff is supported through this interface. You can also do multiple views within the interface, which is really nice for understanding the overall behavior of the system. So here I have saved a layout file previously, so I'm going to go ahead and open that. So this is basically a saved view. Oh, what did I do? I clicked, I think I clicked yes when I should have clicked no. So I'm going to say yes, we want that. No, I don't want to save that. Okay, sorry about that. I only use this all day, every day. So here, what you can see is within TechPlot, you could have multiple frames. You can tile them in all kinds of different ways. In this example, we're looking at particles on the left-hand frame. This is called a slice in the middle frame. So this is a two-dimensional slice that's showing us fluid temperature on the central plane of the reactor. This view on the right, this is what's using, we're using a feature of TechPlot called isosurfaces. And so here we're drawing an isosurface of methane concentration within the vessel. And so, you know, there's a lot of different types of visualization are possible within this interface. And as I mentioned earlier, Barracuda also outputs a lot of text-based data, and so you can do really detailed analysis either with TechPlot's functionality or with Python. And TechPlot also has a Python interface of its own where you can connect to the TechPlot interface with a Python terminal. So a lot of flexibility and a lot of possibilities for digging into the data that's produced. A couple of other things I wanted to point out. One is just the help system that's built into Barracuda. If you've noticed, as we've walked through a lot of these different dialogues, there's always a help button on every page. So if you click that, it will bring up a web browser that shows the user manual for that specific section of the GUI. So Barracuda is very extensively documented. There's a lot of information about all of the different things that are going on for every single dialogue. So that's always there. Another resource that we point a lot of people to is what we call our support site. So if you're on CPFD's website and you have a support account, you can go to your dashboard, and what we'll see here is the newest version of Barracuda is always available for download right from here. So you can download it either for Windows or Linux. There's also a number of training resources that are always available to Barracuda users. Our new user training class, you can either go through that by yourself on your own time, or you can join us for a group training session, which we try to have every 1 to 2 months. So that's a great way to learn about Barracuda. We also have a whole series of TechPlot for Barracuda videos that we've created to show how to do just specific things that are commonly needed. And we also have a series of videos about how to create CAD for Virtual Reactor in case you've never made CAD for this type of CFD model. Other things on our site that can definitely be helpful, and a few of these were pointed out earlier in the presentation. We have this resources tab, and specifically we have a whole collection of publications. So if you're looking for something specific about Barracuda, or if someone has modeled a certain type of system with Barracuda before, we do have, literally hundreds of publications are here, so you can definitely search those and see if anything meets your needs. And then we have done a lot of webinars over the years, so definitely search the webinar collection as well. We also have some videos here from our latest users conference, which we held last June in Chicago, where users from all over the world came and talked about how they were using Barracuda for their simulation needs. So a lot of great webinar content as well. That's all that I wanted to show during this live demo portion. So we'll go ahead and switch back to presentation mode, and I will hand it back to Rosemary.
All right, well, thanks, Sam. So for those of you that are new to CPFD software, I just want to briefly let you know a few different ways that you could get started working together with us. So software licensing is the first method, where your team uses Barracuda directly to set up, run, and post-process simulations. We have a number of different licensing options available, so please contact us and our sales team for specifics, and there will be an email at the end of the presentation that you could use to contact us. Global teams can take advantage of our global enterprise license options available in most countries, and virtual reactor licenses can be served either on-premise or on the cloud, which opens up the door to using both your own hardware and cloud computing resources. We also offer engineering services for those who would like to gain the benefits of modeling your system with virtual reactor prior to building out a team to run the software. So you can also contact us if you want to learn more about that option. And then the easiest way to get started is with our training classes. And our next class is coming up in about 2.5 weeks, and we'll have a little bit more information about that in a couple of slides. And training can be combined with project work and licensing in what we call our Quick Start program, which is intended to get you up and running as quickly as possible. We run the first models for you in-house with our engineering services team, and then we hand the models over to you, train you on the software, and provide the software licensing. And this allows you to build out your own in-house capabilities with models that are already up and running. And lastly, we work with people in a variety of custom ways. R&D partnerships can be direct with us or collaborative with our strategic partners. And so talk with us about your needs if you have any. We also have some upcoming events that we just like to highlight at the end of each of our webinars. Our next new user training class is scheduled for March 6th through 10th. So just please contact us if you're interested in attending that class to get some hands-on experience with Barracuda, and especially after this webinar, if you're interested, just let us know. CPFD will also be attending and exhibiting at AMI Chemical Recycling in Houston March 20th through 22nd. So please stop by if you happen to be there. CPFD will present at the AI City Forum in Houston on March 21st, which is an event hosted by our partners at NVIDIA and Mark III Systems, and we encourage you to attend if you're able. Okay. And also take a look at our events calendars for more information on these and other events in the near future, and I believe that was one of our links that we sent out. So now it's time to answer questions. So I'll be asking the questions and Sam will probably be answering them. And be sure to add any questions that you might have into the box, the question box, if you haven't already, and we'll just get started. Okay, so I'll start with the first question. It's, does Barracuda have a trial version?
Oh, okay, yeah. So we don't have a specific trial version that's just publicly downloadable. However, it is common when people want to start using Barracuda. A lot of times the process that works best is attend a training class, go through that training period. And just to be clear, sometimes people are confused if they have to like travel to Houston or not, because that's where our office is. But no, like in these post-COVID days, what we do is a web-based training class where you have about 2 to 3 hours of your own work each day, and then we do a 1-hour web meeting with everyone who's attending to answer questions and just go through anything that people want to talk about, in that kind of live format. So the training is web-based, and it's kind of a virtual training rather than an in-person, you have to travel to Houston kind of thing. And then, sorry, I got sidetracked. Once you've got that experience, then it often makes sense to do a little bit of a trial, right? Maybe you do like a 2-week trial or something like that, where you can try using Barracuda on your own system, figure out if it's a good option, and whether you want to purchase a license or not after that sort of thing. So hopefully that addresses that question.
Okay, so yeah, and there's a little bit of a follow-up question about the new user training. Is it hands-on training or just a demo type? And if it is hands-on, how do you access Barracuda?
Okay, yeah. So it is hands-on, and as I mentioned, it is virtual, right? So you're not coming to us to use our computers. However, we have started to work pretty closely with a company called Rescale, which is like a cloud computing company. And we found that it's really, really a nice format where we can create cloud machines that have Barracuda on them, and then people use those for the training class. And the nice thing about those cloud machines is that they do have GPU cards. And so for the training, if you're using one of those cloud machines that we've set up, you can have the advantage of running in GPU mode. The examples run really fast. So yeah, it is hands-on, and we find that a lot of people have really enjoyed using that cloud-based access where, Barracuda is already set up. You don't even have to worry about installing it or anything. Some people do prefer to install it on their own machines for training, and that's also fine. But we found that cloud-based access is pretty convenient for most people.
Yeah. Yeah, okay, so we have a few more questions here. So how long does it take to set up a simulation for a typical FCC reactor regenerator system?
Oh, okay. Yeah, so that is a good question. FCC reactor regenerator systems can be pretty complicated, and the full setup time, if you're starting from scratch, a lot of times you do need to take into account the time needed to create the CAD model also. And so in our experience, and Rosemary is our in-house CAD person at CPFD as well. So I think a CAD model creation usually takes something like 1 to 2 weeks if you have all the CAD drawings readily available. And that's like calendar time, right? That's communication and going through details. And then setting up the model could be something like 1 to 2 weeks. So, just kind of realistically, I would say you want to give yourself like that, 2 to 4 weeks of calendar time just to get the model set up, make sure all the parameters are right. And a lot of that time really is information gathering. That's what we find when we work with companies is like, hey, we need this flow rate, we need this temperature, we need this gas composition. So a lot of it is not necessarily sitting in front of the Barracuda GUI typing things in, but rather finding all of those inputs and making sure that they correctly represent the real world system. So I hope that's not too scary of an answer, but yeah, these are big models. We want them to be as realistic as possible. So think weeks, not days or hours. Okay. Yeah, so I think there's a lot of different questions that come in. Let's look at one of these that is related to maybe system requirements first, because I think a lot of people have questions like this.
Okay, so what is the minimum system requirement, like CPU, RAM, etc., on a Linux machine to comfortably work with Barracuda?
Okay, yeah. So this is a really good question, and I just want to point out that you can find a lot of good information on our website, and a lot of times what I will send people back is this system requirements page that we keep updated as new hardware comes out, because there's like new generations of NVIDIA GPU cards every year, new generations of CPUs, things like that. So if you search system requirements, eventually it will return this page. And so what I typically recommend to people is you want to kind of have the fastest gaming machine that you can have for Barracuda, right? You want a really fast CPU like an i7 or an i9 or an AMD Threadripper Ryzen. Typically we tell people to have 16 gigs of RAM. This says 8 gigs minimum. So if you're running small models, 8 gigs is okay. But when we buy machines, we buy like 128 gigs just to make sure that we can handle really big models. And then as I've mentioned before, you really want to have a fast GPU, right? So try to get something like a Volta or Ampere, or they just came out with a generation called Ada Lovelace GPUs that NVIDIA released. So, just go for that latest generation of GPU card, go for the newest CPU with the highest clock speed, and then you're ready to go.
Okay, all right. Well, thanks for pointing out that page too. There's a lot of information on the website if you ever have questions. Does Barracuda accept rate coefficients from a Chemkin file?
This is a feature request that we have on our list, but we have not implemented this yet. So yeah, for people who are familiar with Chemkin, a lot of times they are like, hey, I already have my chemistry in Chemkin. Currently, it's not supported for that. However, one thing to note is that Barracuda project files are text-based. And so we have had users who have done things like scripting where they say, okay, I'm going to kind of transform one text file into another text file and create a Barracuda chemistry set. So I know, of course, I really love scripting, so that sounds like a fun task to me, but I know that may not sound like fun to other people.
But it is possible.
It is possible, yeah. Okay, how about this one?
Okay, is it possible to incorporate both stoichiometric and species reaction types into a project? For example, insert some reactions using stoichiometric reaction type and then the rest using the species reaction type.
Yeah, definitely. So in this example, I happen to show just all volume average stoichiometric reactions. However, it's perfectly possible to mix and match species and stoichiometric, right? So that way you can have, for example, 5 that are stoichiometric volume average, 5 that are discrete, and they can each, do what's best for each reaction, right? Make sure you use the appropriate ones.
Okay. All right, and can Barracuda Virtual Reactor model Lagrangian solids and gas bubbles simultaneously in one simulation?
Absolutely, yeah. So the ebulated bed example that Rosemary showed earlier in the presentation, that is a bed that includes a liquid domain and then a whole bed of solid catalyst particles, and then also gas bubbles traveling up through the bed. So yeah, definitely, it's a 3-phase sort of simulation there.
So it is possible.
Yep.
Okay, so how does BVR use parcels instead of particles in the NPPIC model?
Oh, okay.
Yeah.
I see. So here, let me go back to maybe this slide. I'm just going to pull over the PowerPoint so we can slide up to there. Because I think this question is kind of in reference to this.
Okay.
So what Barracuda is really doing is it does use this idea of parcels, or what we call clouds from MPPIC for multiphase particle and cell. And really, it's not feasible to track every single physical particle in a huge system, right? Like big chemical reactors like FCC regenerators, they have something like 1 e to the 16 or e to the 17 particles. And on today's computers, you just can't track every single one of those individually. And so what we do with Barracuda is we use clouds. Each cloud represents a collection of identical particles. And so what we can say is, all right, this cloud represents so much mass of a particle with a diameter of 62 microns and a temperature of 800 degrees Kelvin or whatever, right? We're tracking all these properties for the cloud, and then we calculate the physical changes that the cloud would undergo in terms of position and velocity and acceleration and composition. And then all of those changes are assumed to be applied to all of the particles represented by the cloud. So it's almost like an inverted approach to what people do with CFD models, right? Typically the CFD model subdivides a big space into little boxes, and we solve the equations on the little boxes. What we're doing now for the parcels is we're grouping a bunch of physical particles into a cloud and solving the equations for that cloud. Are there any other questions that are standing out?
Yeah. Do you provide model build services in addition to licensing the Barracuda software?
Yeah. And so as Rosemary mentioned on on this slide, CPFD does have an engineering services team. And so the job of the engineers on that team is to work with clients who maybe don't have a Barracuda team in-house. They don't have the software experience. Maybe they don't have a CFD team at all, right? That's pretty common for a lot of people who run chemical reactors. They don't necessarily have a bunch of CFD people sitting around. So we do have a team of CFD people, and they use Barracuda, again, all day, every day to run models that people want to get the benefits or the engineering benefits of Barracuda without having their own in-house CFD team. So yeah, if you're interested in that, definitely email us at that info@ email address, and we'll be happy to talk to you about that.
Yeah, and we also have the Quick Start program where we basically do like the first phase of a project for you, and then we hand over all of the materials to you, and you license the software, and then you can take it from there. So that's real nice for doing some like parametric modeling or studies.
Yeah, definitely, definitely.
Yeah.
We have time for a few more questions, I think, here. I see one here that's kind of interesting.
Okay. Would it be overkill if we don't have reactor modeling, just particle flow?
Okay. Yeah, so if I understand this question, this is saying like, what if I don't have chemical reactions, but I do care about the hydrodynamics of the system? And so, yeah, we have a number of customers who've used Barracuda over the years and who still use Barracuda for pure hydrodynamics models, right? Sometimes we refer to these as cold flow models if they just don't have chemical reactions. Sometimes they don't even have thermal aspects that are really important. But Barracuda can still be really useful, right? If you have a big industrial system where the particle fluid hydrodynamics are important, then Barracuda can definitely be used for that. So definitely talk to us about that.
Yeah, and how about slurry bubble systems? Can they be analyzed? Is it a Eulerian-Lagrangian approach or Eulerian-Eulerian approach? And can we model bubble coalescence and breakup? Sorry, that's a couple questions.
Okay, yeah, that's fine.
They're kind of all together.
Yeah, no problem. So yeah, the slurry flow is, if I understand correctly, could be something pretty similar to this system, right? It was this ebulated bed system. This is still an Eulerian-Lagrangian approach, right? So when we look at this particular image, the image on the left is showing Eulerian-Lagrangian in the sense of the liquid domain is Eulerian and the particles are Lagrangian. And the right-hand image is still the same in the sense that we have this Eulerian liquid domain and the bubbles are Lagrangian. So just be aware of that. Both the particles and the bubbles are kind of using a similar Lagrangian approach behind the scenes to model what's going on. The last part of your question is related to a feature that we are working on. It's not released yet, but we know that this is important to people, right? To be able to do bubble coalescence and bubble breakup. So that's something that we are working on from a physics standpoint. And so hopefully in the next few releases of Barracuda, hopefully we'll get some more capabilities in that aspect of things.
Okay, yeah, I think we have time for one more question. And then if you asked a question and we did not have time to get to it, we will be emailing you in the next day or so. And also if you put in a question during your registration and we didn't answer it, we can also, we'll be emailing answers to those questions. Do we have an example of simulation validation, like comparing with the real thing, like comparing with experimental values? I think is what.
Yeah, for sure.
Yeah.
So again, I would point you to the website because if we have a story to tell, we're always happy to tell it. And so the stories that we have to tell for that would definitely be on the webinars page. Mm-hmm. Oh, and I just clicked kind of away from it, but a lot of these stories, right? If you look at the presentations that people gave at the Barracuda Users Conference, a lot of our users are talking about how they compared the Barracuda results to their real systems, right? Because typically almost all the people that you see presenting are people who work at big companies that are running reactors all the time, and they're using Barracuda to model real systems and compare the results. The other ones I was looking at were maybe some older ones where I know we've talked about things like big FCC projects that we've done. Here's one of our distributors talking about a cement plant revamp, right? We've told a number of these stories over the years. And a lot of these webinars are probably the most accessible way to learn more about those.
Yeah, yeah. All right, well, we thank you so much for joining us today. Again, we will send out an email with the link to the posted recording, and then we'll also answer any questions. But if you have any questions that were missed or were not answered, feel free to email us. You can email us at info@cpfd-software.com, and we'll be happy to hear from you. Thanks so much.